Thank you. So I'm going to revisit a question that has been asked before, and that is, can it help knowing that there is just few solutions to an NP-hard problem? On one hand, your intuition tells you that if there are more needles in the hay, well, then it should be easier to find one, right? But there could also be that one needle forms kind of a structure.
Could you move your microphone higher?
Yeah, okay.
I got it.
Okay. Yeah, do you hear me now? Yeah, okay. So you can imagine that there is some kind of structure that will guide the search and make it easier to solve the problem if there's just a few number of solutions. So, but like I said, this has been studied before, and what we know is that it cannot help too much because there is this reduction by Valiant and Vasirani that if you can solve unique set really fast, like 2 to the n to some little o of 1 time, then the randomized exponential time hypothesis is false. So this means that for every NP-hard problem that has a parsimonious polynomial time reduction from satisfiability, uniqueness cannot help you a lot. If we look at satisfiability alone, then it's even worse because uniqueness doesn't help at all. So if you have just a slightly faster algorithm for unique set, then you also will have one for the general case. So the strong exponential time hypothesis in a randomized sense will be false. But perhaps uniqueness helps for other NP-hard problems, and this is what I'm going to talk about today. I think it makes sense when we look at this fine-grained perspective of things, and this is 2 candidates that we've come up with where uniqueness might help. So the first example is finding a Hamiltonian cycle in a directed graph, and here I look at the runtime parameterized by the number of vertices, or finding a vertex k-coloring in a bounded degree graph parameterized by the path width. So the general paradigm I use for algorithms that benefit from few solutions is that I, in the first step, make a connection between the wanted objects, the solutions to the problem, and something else that is more easily counted. So I turn apples into pears, and then I count the occurrences of the pairs and deduce from that outcome if there is a solution or not to the original problem. So we will see these 2 examples of this paradigm. So remind you of what is the directed Hamiltonian cycle problem. You're given a directed graph, and you want to find a tour visiting every vertex exactly once. So for this particular instance, there are 2 solutions. So this is the first apple, and this is the other one. But we're not going to count apples directly. We're going to count pairs. So our pairs will be vertex partitions with certain constraints. So we will look at partitions of the vertices in 3 groups, X, Y, and Z, which will be red, green, and blue, respectively. And the vertices in X are special because they need an odd number of arcs ending in the other parts, whereas the vertices in the part Y must have an odd number of arcs ending in Y, and the same holds for Z. And because of this symmetry in Y and Z, we only count one of the 2 solutions obtained by switching the role of Y and Z. So this looks like a strange problem, a strange partition problem that is not directly related to Hamiltonian cycles. But we showed that the number of Hamiltonian cycles and the number of such XYZ partitions actually are equal modulo 2. And I will not bother you with the proof now. It's pretty straightforward, but still there is no understanding from looking at the partitions how they really relate to the cycles. But nevertheless, we will see a few beautiful, colorful pictures here to demonstrate this. So if we look at the instance we had with the two Hamiltonian cycles, this is one such partition. You see here that all the green vertices has one and only one neighbor in the green, and the blue has one and only one neighbor in the blue, whereas the red has one neighbor of the other kind, like this. So that is one such valid partition. It turns out that there are 8 such partitions altogether, and it's hard to see some structure here related to the Hamiltonian cycles, but still these are the partitions, and we note that this is an even number, and remember the instance had an even number of Hamiltonian cycles. So if we take the instance we had and just flip one arc so it goes the other way, we destroy one of the solutions and we're left with only one apple. So if we take this instance instead and look at the partitions, we have another example. So here again you see that the green ones has just one neighbor, and the red one has like one neighbor in the green side. And it turns out that there are only 3 such partitions here, which is an odd number. And remember, the instance had an odd number of solutions. So this means that potentially we can attack the parity problem for Hamiltonicity by counting these partitions instead. But we're still in problem because, I mean, counting the partitions, there are 3 to the n of them. So just doing it like a brute force fashion won't work. So we need a better idea, and that idea is we count the partitions by first finding all possible parts y. So all possible green parts that can be part of any partition. And if you remember, the green vertices, the y vertices, needed an odd number of neighbors in itself. And if you do the following trick, that you add a self-loop to the vertices, uniformly and independently at random, we can make the probability of a vertex being in a green part independent of the other ones. And adding a self-loop doesn't affect Hamiltonicity, obviously. You can never use a self-loop. So if you count this, you get that there is 1.5 to the n y parts in expectation, but it's not that easy because we also need an algorithm that lists them efficiently. But we figure out how to do that in the golden ratio to the n time. So we can actually list these green parts. And once we have the green parts, we can use a linear algebra to count the number of partitions for the remaining vertices in the 2 parts x and z. So that is just Gaussian elimination and looking at the rank. So this means that we get a 1.618 to the n time algorithm that will see if there is, can separate the case when we have one Hamiltonian cycle or no Hamiltonian cycle. And if we augment this with a recent result with Bell and Husfeldt. There's a parity lemma, which essentially just flips a biased coin for each edge to see if I should keep it or not. And then with a certain probability, there will be an odd number of solutions, depending on how many solutions there were to begin with. We get this n choose k times 1.618 to the n time algorithm, if they have at most 2 to the k Hamiltonian cycles. So this means that we can have an exponential number of Hamiltonian cycles and still beat the 2 to the n time, which is the best known general algorithm for the directed case. There is some progress. Sigan et al. Showed like 3 years ago that for bipartite directed graphs you can do 1.9 to the n, essentially. Still, we don't know what is general directed case. So here you can think, what does this mean if we're thinking in terms of, can we prove a Seth's lower bound on directed Hamiltonicity? Well, then it seems like you will need the reduction to make the number of cycles a lot of them. So it gives some hint on what that reduction would look like. Okay, so that was the first example. The second example is k-coloring, and let me remind you again what is the problem. You have this undirected graph, and you want to put a color on each vertex from a palette of k-colors. And in this particular instance, there is a unique 3-coloring, unique in the sense that up to permutations of the colors, there is no other coloring. So this is the only apple for this instance. But again, we're not going to count the apples, so the pairs here will be subgraphs, and we will orient the edges of the graph, making it a directed graph, and we will also add vertex degree constraints. And we will count subgraphs such that the difference between the outgoing arcs and the incoming arcs equals the constraint on the vertex for every vertex, counted modulo k. So this is how k enters into the equation here. And we also say that the subgraph is even if it uses an even number of arcs and odd otherwise. So what is the connection between apples and pears? Well, it turns out that for any orientation and any choice of degree constraints, if you can't color the graph with k-colors, then it has the same number of even and odd such subgraphs. And this is basically the Alon-Tarski theorem, if you just tweak it a bit. But the more interesting part is the second one, which shows that for any orientation and at least a fraction 1 over s of all the choices of these degree constraints, a k-colorable graph, which has s, a positive number s of solutions, will get a different number of even and odd such subgraphs. So again, I will not give the proof, but rather show these colorful pictures. So this is how the instance could look when you have putting an orientation on the edges and added some modular degree constraints. So remember, we're looking at 3 colorability here. So the constraint is either 0, 1, or 2. So what does an even subgraph look like here? Well, even means that it uses an even number of green arcs here, so you can count them, and you can see that there are 10 of them, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes. And if you look at the degree constraints, you remember that the number of outgoing arcs minus the number of incoming should be equal to the degree constraint. So here it is 2, because there are 2 outgoing arcs. Here it is 2 because there is one incoming arc. So this is where the modulo 3 arithmetic comes in. So up here there was 1 outgoing. You have examples of 2 outgoing. You have more interesting examples here when we have a cancellation between 2 and then 1 going out, and so on. So it turns out there are 3 even such subgraphs. So what about the odd ones? So an odd one here will use an odd number of arcs 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, you see this, we have 2 outgoing, we have 1 incoming, 1 cancels and 1 outgoing, and so on. And it turns out that there are 6 of these. So this is a different number of even and odd. So I could, if you remember my connection, you can conclude that it is indeed a 3-colorable graph. So what if we destroy that property? If we add a single arc, and remember the original instance was uniquely 3-colorable, so by putting an arc between 2 vertices that had the same color in that coloring, we are forcing a 4th color, the gel one, but we keep all the degree constraints. And if we look at the even and odd subgraphs, of course we have all the old solutions, but we also have a lot of new ones. So it actually turns out that there's a 20 even and there's 20 odd here. So we have broken the 3-colorability property, and thereby we end up with this balanced situation. So what does this mean algorithm-wise? How can we use this to make a faster algorithm? So I will first briefly mention the concept of path decomposition. It basically means that you can think of the vertices order from left to right, and you're sweeping a bag which contains all vertices which has dependencies to the vertices to the right. And in that bag you encode information of how you partially can color the graph, the part of the graph that you've seen. So this natural algorithm, which uses for each way of color the subgraph that we've seen so far, we tabulate for each way of coloring the bag if this is possible or not. So there is k colors to choose from, and the path width is the size of the largest bag needed. So you will need k to the path width number of states sweeping from left to right here. And this is something that people have thought about. Maybe we can do better than this. But it turns out that probably we can't. So not too long ago, Björklund and Mike Sansara showed that you can't even go slightly below this k to the path width. Every positive EPS below k will imply that the strong exponential time hypothesis is wrong. So that's it's a bit of a downer for us, so we have to do something to get around this. And what I suggest is that, okay, let's look at bounded degree. So if we also assume that every vertex has degree bounded by d, and we're looking for a k-colorability for some k that is larger than half of this max degree. This is still an interesting problem because it's already NP hard to 3-color a degree 4 graph, and this comes from the Hollier's proof for edge coloring, and you just take the line graph, that construction. And once we have gotten to this, and we're we're counting these subgraphs instead, we're in a situation where for each vertex in the bag, it suffices to remember what is the current in out degree minus in degree situation, but we can forget all configurations where there is no possibility to patch up a valid solution with the remaining arcs. So this is sort of a meet-in-the-middle algorithm. So you can throw away a lot of the states here. So this means that we end up with a d over 2 plus 1 to the path width Polynomial-Time algorithm. And remember, k was larger than this by assumption, and then we have something that is exponentially larger, exponentially faster than the natural algorithm. And even assuming such a max degree bound, I don't think it is known how to elsewhere improve on this k to the path width natural algorithm. So that was pretty much what I had to say. So this is just the references. Thank you. Mike?
Your pairs seem kind of magical. How did you think of them?
I don't think of them. I work with equations and see what ends up, what I end up with.
Backwards from the equations?
Yeah, so start with things like inclusion, exclusion. Yeah. I agree. I mean, in retrospect, it seems odd that these are related. Yes.
So there is some kind of a method you can work backwards from the equation.
Yeah.
So what's your guess? Is it going to be somewhat easier for the general coloring, for the general graphs? The unique case is going to be easier or equally hard?
Yeah. I mean, this is my question to you. Is this just some intermediate results where there is actually a general algorithm which is as fast or even faster than I showed? Or is this a symptom? Something that we haven't seen before, we haven't looked at this scale before. Not for these problems, for satisfiability we have.
But Mohan, your intuition is the opposite, right?
I don't know. I don't know about coloring that much. I haven't thought of coloring.
Okay.
Satisfiability.
Yeah. But this is as close as disagreement as we ever get, right? Actually having opposing intuitions about whether or not the number of solutions makes it easier or harder.
So we're close to the fight you mentioned earlier. Yes.
I think you can make any kind of general comment of how to turn, say, these kind of natural permutation problems, as in a sense Hamiltonian cycle is, in a sense,
Yeah.
into something which uses these kind of partitions, because they lead to a single exponential time instead of, well, kind of.
Yeah. So maybe there is a more general principle here. If you remember the first example, we turned subgraphs into partitions. And in the second part, we turned partitions into subgraphs. So maybe there is some more general structure here. I don't know.
Okay, so I understand that.